Hi everyone, my name is Lydia and this is what I wish they had taught me about econometrics and introduction. In this video, we're going to talk the math behind OLS. Now, I know that most of you already have either the books or plenty of other resources that show you how to make and how to do the proof and how to do the math with finding the actual formulas for the beta null and the beta 1. However, in this video, I'm going to go a little bit slower and I'm going to concentrate on the math elements that you need for every single step. Because sometimes some of these steps that show you the OLS proof might be skipped, and I know that there are a few steps that are not directly clear to the students. So the aim of this video is to show you exactly those little tricks that are used so that it makes it a lot more easier for you to follow your class teacher or lecturer in class. Okay, so before we jump into that, remember what we're trying to do is to find, is this my best line, or is this my best line, or is it this the best fitted line? So we have a lot of candidates in here and we need to find which is the best one. And let's say through computations, maybe we will find this particular line. And for every line, we need the slope and the intercept. Okay, so most of the times you have two ways of actually drawing a line. It's either you have two points and you can connect them, or you simply need the slope and the intercept information and you can easily draw the line. Well, the OLS is exactly the math behind the computation of the slope and the intercept so that you can easily draw this line in the end. Now, keep in mind, at this stage, we have all of these candidates in here, and we don't know yet that it is the highlighted one, that it's the best one. So let's see what's the process into getting to the part where we can say the highlighted one, it's the best one. The problem that we are going to solve is the minimization of the sum of the residual squared. And keep in mind, the residual we have defined as the difference between your true observed y and the estimated predicted y. Okay? And because we are looking at the predicted yi, keep in mind that in the previous videos, we have defined the predicted line yi as equal to beta null hat plus beta 1 hat xi, and we have clearly emphasized that this beta hat, this beta 1 in here, they are actual numbers that we have finally managed to compute, which means like I know this too, guys, and I can have my line drawn. That's why, because like the betas are most of the times like associated with the fact like what you have estimated, you always have the hats to associate with those. You might be a little bit thrown off if you see, for instance, a minimization problem where it gives you like the beta 0 and the beta null is actually Latin letters B0 and B1 like this. If you ever see this kind of notation, and keep in mind, it is very easy that you might see it as beta 1 and beta null. However, if you see it as B0 and B1, it just means that at this stage right here, I am just theoretically thinking about what is my best fitted line. And so once I do my computations, I will get to this beta 0 hat and beta 1 hat. Also, keep in mind that there are other sort of conventions, and most of the times the betas, we associate them with population parameters. So in any of those cases, make sure that you read very carefully the context and the information that is given to you in the exercise before you use the notation that it's best appropriate for this particular case. Okay, so for the purpose of this video, though, we're going to start thinking that beta 0, beta 1 right now, B0 and B1 right now are some theoretical candidates that we have in mind for fitting of the best line. And the moment that we turn into the actual computations and we get the actual numbers, we're going to call them as beta 0 and beta 1. The minimization problem in here, as any other minimization problem, will do the first order conditions. They need to be done with respect to B0 and with respect to B1. This is usually the computations that you will always see in any resource given to you. Some of you might very clearly see what's happening in here, but for those of you that are not very familiar with OLS and are just getting into it, I'm going to remind you of derivative rules, okay? So whenever you are doing, for instance, the derivative of 2x, you know that this derivative is simply 2. And you know that if you had the derivative of 2x cubed, for instance, you know that this derivative is 2 times 3 times x squared. Okay, and you can go to higher powers and so on. However, things change a little bit though the moment that we have a derivative that is of the shape 2 times x plus 3, or let's say 2x plus 3 to make the point, all squared. Okay, in this particular case, we have to be a little bit careful. So as usual, we have the 2 in here, and then the 2 of the power that goes down. And then we have the 2x plus 3, which remains at the power 1. And ultimately, we have to add one more element, and that is the derivative of whatever is inside the brackets. So ultimately, keep in mind, so this 2 is the 2 that we had in here. This other 2 is the power that came down. And here now we're left only with power 1, 2 minus 1. And we also need the derivative of whatever is in the brackets. So ultimately, the final value of this derivative is going to be 8 times 2x plus 3, and you can further work it, okay? So most of you might have seen that if you have like an expression u and it is to some power n and you need to find the derivative, well, the generic shape of it will be that it's n times this u expression at the power n minus 1 times the derivative of the expression u by itself. Now, this concept, this formula is exactly the same one that is used for the first order conditions of the OLS. So that's why in here you will see the 2 that comes in front of the summation notation. It's the 2 that we have in enveloping basically the entire expression. Like you can think of this one as your expression u, okay? Now, where does the minus in here come from? Well, keep in mind, we're doing a derivative with respect to beta null, okay? So to B0. So it means that when we find the derivative of the actual u expression, we're finding the derivative with respect to B0 in this particular case, and we can clearly see that there is a minus. So this minus is the one that coincides with that, okay? The rest of these steps are clearly then straightforward. We simply get initially rid of this minus 2 by sending it to the other side. And then ultimately, we simply split the summation notation by applying the properties of the summation notation being a linear function. Okay. So that's why we're going to have here the sum of yi minus the sum of beta null minus the sum of beta 1 hat xi. Now, notice something else while I am doing this derivation. So as I said, the B0 and the B1 in here, they are entirely theoretical whenever I'm thinking of like minimization problem. However, the moment that I jumped into the first order conditions, that means, oh, now I'm working with actual numbers because I know that at the end of this derivative, I'm going to get the numbers that I wanted. And that's why we swapped them to beta null hat and beta 1 hat. Okay, to signify that we will get eventually to those particular numbers. Okay. The next steps will require having some knowledge of the summation operator. And this is what now the second reminder will be about. Okay. When the summation operator, it's a bit of a loop, right? So that means that whenever I have a loop that starts from 1 to n, I am of some I in here. It means I am going through the first loop. My I takes the value of 1. And then I need to keep adding because then my loop will jump into 2. And then I will have to move into 3 because that's when my loop will move into 3 and so on. Okay, so this is my entire sum. Now, of course, if I have here the sum of xi instead for I going, let's say, from 1 to 4, then I can easily see that I have x1 plus x2 because on the next loop my I becomes 2 plus x3 plus x4, and obviously it ends at 4 because I only put the loop until 4. Okay. The thing that most students find difficulties with, though, is this last property of the summation operator, which is what we're going to use quite a bit in the proofs for solving the first order condition. If you have the sum of a constant, let's say 1, and the loop goes from 1 to 3, keep in mind, in this particular case, your sum is 1 plus 1 plus 1. So it's 1 3 times, because every time my I is updated, however, there is no other place where I can apply that update. So that's why it's all the time 1 plus 1 plus 1, which means I just have a 3 in here. Okay? Ultimately, this is not so much of a property, but just a reminder of the fact that the average formula is that if I have the average, let's say y bar, this is the sum for I from 1 to n of all of my y's divided by n, which means that I can rearrange this and rewrite the sum of all of my yi's as equal to y bar times n. Okay, I would like you to remember these two because we are going to use them extensively in the proofs. With this reminder being finished, let's go back to the expression that we had over here, and let's try to see how each of these elements is being applied. Okay. In the first one, we can clearly see that this is the reminder in green. So this is where the formula of the average will need to be used. So we're going to have n y bar. Then for the second one, in here, you've got the sum of the beta null. Now keep in mind, beta null doesn't have an I, which means that it is just a constant. So this constant is going through the loop and times, and it means I'm just going to write it as n times beta null. Okay? And lastly, I have the last element in here where I have a constant and I also have a variable that is going to change because I have the xi. In this case, I can use both of the two properties together and I can rewrite it as simply, change the color, as simply minus n times beta 1 hat times x bar. And that's going to be equal to 0. Okay. From here, we can easily see n being common to all of them, so we can cancel it out, and ultimately we're left with y bar minus beta null hat minus beta 1 hat x bar equal to 0. Rearranging it, keep in mind we started this first order condition with respect to beta null, so beta null hat is what we have to find, and that is y bar minus beta 1 hat x bar. So this will be the formula for our intercept, the beta null hat. Thank you for following the math for the first part, which is finding the intercept. And in the next video, we'll show all of the tricks behind the math of the derivative with respect to b1. See you in the next video.